Moving on then to taking the quake W results into slope W and to sigma W to look at post-earthquake stability and to look at permanent deformation. So we want to take these results into slope, and we want to consider the effect of the strength loss and the excess pore pressures on the stability. And then we want to take the results into sigma to look at permanent deformations, once again taking into account the effect of the shear strength loss and the excess pore pressure in a sigma W stress redistribution type of an analysis. So here is what we're aiming to do, is a stability analysis, and then I want to show you how we can make a graph as to what strength is being used. And then finally, we want to look at the post-earthquake permanent deformation, particularly the displacement field. Going back to GeoStudio then, going back to the define view, under key-in analysis, we now need to clone our stability analysis that we did before the earthquake shaking. Everything else should be the same. The geometry and the extents of the trowel slip surfaces will be the same. So the first thing we need to do is we click on the before downstream stability analysis, and we clone this analysis. And let's call this after. Downstream stability. Now in this particular case, we want to get the initial conditions from the dynamic quake W analysis. So the dynamic quake W analysis will become the parent. And when we do a quake W analysis, at the end of the shaking there are always some numerical residual dynamic stresses. In real life, they no longer exist. All dynamic stresses have disappeared. In order to get rid of any residual dynamic stresses, for a stability analysis, we say that we want to get the stresses from our parent, but we want to use the stresses for the initial conditions. However, we want to get the pore water pressures from the last quake result. So this is very important. We want to get in our type of analysis, first of all, we want to do a quake stress type of stability analysis. Once again, our parent is the quake dynamic analysis. We want to get the initial stresses from the initial stresses, which represent the static stresses, and we want to get the pore pressures from the last saved result from the quake analysis. So we are doing a slope W stability analysis using quake W stresses. We are using the parent, the quake W analysis, as the parent, and we want to use the initial stresses from the parent, representing the static stresses, and we want to use the pore pressures from the quake analysis, the last of the analysis that were saved. Now we can do the same thing for our upstream. Once again, we say click on the upstream and we clone this result, calling this now after upstream stability. Once again, our parent is the dynamic quake W analysis. We are going to do a quake stress type of stability analysis, and we get the initial stresses from the initial conditions, and we get the pore water pressure conditions from the last, or the 10-second value. There's a repainting problem here, but if we close it and reopen it, we will be able to see it. It's the 10-second or the last result that was saved. I'll just open it once again so that it is visible here. So to repeat then, our parent is the quake W analysis. We're doing a quake W stress type stability analysis. We are getting the stresses from our initial conditions, and we're getting the pore pressures from the last saved quake W fall. Going to the defined view then for the downstream, we see that our extents, everything is the same for the upstream, and we can now compute the factors of safety for the post-earthquake. Before we do that, we need to make a change to our materials. And so we say key in materials, and we have a new material here called foundation liquefied. It's a different material. Everything is the same except the liquefaction parameters are now different. The liquefaction parameters are now different. We have assumed that all of the elements that were marked yellow or potentially liquefiable, that we would fall down to the undrained steady state strength. So notice that the collapse surface angle here has been set to 0, and the undrained steady state strength is the only component of the strength that we will now use post-earthquake. So this is, in order to do that, we have to define a new material, all else being the same, except that we have different liquefied strengths. We therefore, in our stability analysis, have to say draw materials, and we select foundation liquefied and assign the liquefied material to the foundation for both the upstream and the downstream. Draw material liquefied. And we now should be ready to compute the post-earthquake factors of safety. And now we see that if this foundation had indeed liquefied, we would have lost stability in the downstream direction. In the upstream direction, we would have still maintained stability, and the factor of safety has fallen, but it has not fallen all that significantly. So our main engineering issue here is downstream stability. And we can see that the slip surface wants to go very deep. And the reason for that is that the slip surface is extending into the liquefiable zone. Unfortunately, I cannot show the liquefiable zone in slope W, but what we can do is we can look at the strengths that have been used along the critical slip surface with draw graph. And if we plot the cohesion versus slice number, and we plot the friction versus slice number along the critical slip surface, and we plot these two things together, we see that we have where the slip surface is within the embankment and the crust, we have our typical frictional properties together with a C prime of 10 kPa. Then, however, as the slip surface enters the liquefied zone, the frictional component drops to 0. This is the frictional component. And all we are left with is an undrained strength of 10 kPa. Then as the slip surface comes out of the zone that has been marked yellow, then we are now no cohesion. We have our frictional component again, and we have our conventional strength in this area here. But the point of interest is this zone here where the frictional component has dropped to 0, and all that we are left with is the undrained steady state strength. Now perhaps I should have extended my enter region here of my trial slip surfaces, because it looks like my critical slip surface is right on the edge of the enter regions or distance. However, I have not put any more effort into it because I'm already less than 1, and even if I were to compute a factor of safety that is lower than 0.878, it wouldn't alter the conclusion that I have lost stability. Now I could do that, but my conclusion as to the meaning of the analysis obviously would not change. And so we can see now that we have fallen from prior to the earthquake on the downstream side. We had, on the downstream side, we had a factor of safety of 1.88. As a result of the strength loss, together with the generation of excess pore pressures, we have lost stability of this structure. Now at this point, the question becomes, I have already lost stability. The game is over, so to speak, and if indeed this structure were to be subjected to this earthquake, then we would have complete collapse of the structure potentially. So why do a permanent deformation analysis? And that is a legitimate question, but nonetheless I will go through the process here just to illustrate the procedure. So let us go back to the define view. Under key in analysis, we now want to add a sigma analysis, and we want to add a sigma stress redistribution type of analysis. A sigma stress redistribution type of analysis. Once again, our parent is the quake analysis. Once again, we want to get our stresses from the initial static conditions. Going back to key-in analysis, and we want to get the pore water pressures from the last quake W analysis. The same as for the stability analysis, we now want to have the initial static stresses and the final pore water pressures. The analysis type is a stress redistribution, and our parent is the quake W dynamic analysis. Now we have to, the first time that we are doing a sigma analysis, we have to, we did not clone it previously, so we have to assign our materials, say draw materials, and we have a dam embankment material, we have our granular drain, and we have our surficial crust. And finally, now we have our foundation liquefied. And we should now be able to do our stress redistribution analysis and look at the resulting deformations. When I clicked on the start, an error message popped up, and the reason for that is that I had forgotten to apply boundary conditions. So let us apply a boundary condition, and we will fix the base of the problem again, and we will fix the ends of the problem as well. Clicking on Verify, suggesting that I have supplied sufficient information this time, clicking on the Solve window and solving the stress redistribution. And now we can go to the results view. I will turn off some contours here for the time being, and we can look at our deform mesh. So what we have here now is that this is a representation of the permanent deformation. And a convenient way of simply looking at what is the maximum of deformation, we can say draw vectors. And we see here that the maximum deformation that has been computed is about 50 millimeters. Not a large amount, but once again, as in the lower San Fernando Dam, the actual amount of deformation here probably is not all that significant and meaningful, because the stability analysis indicated that we would have already lost stability. However, the displacement field is still of interest nonetheless, and perhaps in this particular case here, viewing the displacement as vectors is probably more meaningful, and so let's look at it as vectors instead of a deformed mesh. And so here is our displacement field. And obviously this is quite believable that this would happen, and this is somewhat consistent with the stability analysis, suggesting that there is a critical slip surface that goes something like this. And so it also suggests that if there was a failure, it would be downstream. It also suggests that there would probably be very little movement in the upstream direction, also consistent with the post-earthquake deformation stability analysis upstream, which indicated a large margin of safety against sliding in the upstream direction. Now, I've already noted that perhaps the computed post-earthquake permanent deformation, the magnitude is not all that meaningful because slope stability analysis indicated we had already lost stability. However, the displacement field is very meaningful and realistic, and at this stage you could try altering your undrained steady-state strength, and if we were to cut it in half, we would likely get substantially more permanent deformation because, as I've noted earlier, the amount of deformation you compute is actually somewhat sensitive to the assumed undrained steady-state strength. I won't do that here. You can do that on your own, but from a practical point of view, if I lower the undrained steady-state strength, then the factor of safety would also fall even lower, and since it is already less than 1, there is not much value in doing that type of parametric study. However, it would show you the changes in the permanent displacements if you were to alter the undrained steady-state strength. This brings us to the end of our illustrative example, going back to the defined view and just summarizing what we've done here. We started with a sigma W initial in situ stress analysis. We looked at the stability downstream and upstream before the shaking. Then we did a dynamic shaking analysis, and then we looked at the downstream and upstream stability after the earthquake shaking. And finally, we did a sigma W stress redistribution analysis to look at the possible permanent displacement field. Now, this example, as I noted at the start, may not be all that realistic in many respects, and nothing should be read into the actual results that we have computed here. The example was simply set up to illustrate features, techniques, and procedures. And I think we have accomplished that here now, and that brings us to the end in using this example to show all the types of analysis that we can do and the steps that are necessary in doing a dynamic analysis and the steps that are necessary to do a liquefaction assessment and the detailed discussion on the implementation of the collapse surface concept and how vitally important it is in the idea of a liquefaction assessment. So I will leave this illustrative example at this stage here and proceed on to some other more miscellaneous topics in using Quake W.